Okay, in this lecture, we are going to compute the mean, variance, and cumulative distribution function for some of our familiar distributions. These are all going to be discrete distributions in this case, and in fact, so far, all we know are the Bernoulli distribution and the binomial distribution, but we'll probably also get to the geometric distribution by the time this is all over. Okay, so the Bernoulli trial is a situation, really, where we're going to have a very specific distribution for a random variable x, and that random variable takes values of 1 and 0 if our trial is successful, and 0 otherwise, like this. And the probability that the value of the probability distribution is defined in a similarly conditional statement that says the probability is equal to p for the case where x equals 1, and 1 minus p for the case where x is equal to 0. Okay? So this defines the whole distribution. We can summarize this, of course, in this table. The table looks like this. Lowercase x, we're talking about specific values here. Big X in the subscript, little x in the parentheses. Okay? So I get a lot of questions about which goes where. So outcome 0 would have probability 1 minus p, and outcome 1 will have probability p. All right? So if we wanted to compute the mean of this distribution, then what would we do? We would take the mu sub x, this is the definition, is the expectation value of the random variable x itself. And so what we're going to do in order to compute that is to compute the sum over all the possible values that x can take, and we're going to multiply x by the probability of seeing that value of x. And this ends up being pretty simple. The case where little x is 0 vanishes. The case where little x is 1 just gives me p. And so the answer is p. Okay? If I were to really write this out laboriously, I would have 0 times 1 minus p plus 1 times p. Messed that up a little bit. 1 times p, like that. All right, so that's where it comes from. All right, so what if I wanted to compute the variance for a single Bernoulli trial all by itself? That variance, by definition, would be the expectation value of my random variable x minus the mean of that random variable x, and I would square it. Okay? Now, of course, there's a computational formula that makes this easier in cases where you have lots and lots of outcomes. Okay, so if you have a whole bunch of possible values of x, it makes a lot of sense to go to the expectation value of x squared minus the expectation value of x and then square that. Okay, that's your easy computational formula. But in this case, it's always nice to keep in mind that this is really what the variance is doing, is taking the expectation values of squared deviations from the mean. So let's go ahead and take let's go ahead and do this by explicit evaluation of the sum. So we have, again, our sum over possible values of x. We have whoops, that's the wrong one. That's the wrong x. Okay, so I make these mistakes myself. This is the value of x minus the mean value of x, and I'm going to square that, and then I'm going to multiply by the probability distribution at that value of x. And this is reasonably easy to evaluate, but it takes some thinking perhaps. Okay, so we have x equals 0 and mu x equals 1. So this is going to be minus p squared times the probability of that x is equal to 0 is 1 minus p. And then we have that added to the outcome when I have 1 minus p. Okay, that's x equals 1, mu x is always equal to p. Then I multiply that by the probability that x is equal to 1, and that was p. All right, so we do some simplifications here. A couple of things factor out. We'll get a p. Whoops, I don't want to factor out a p squared. I want to factor out a p. And then I'm going to get the minus 1's just become a positive 1 here. So I get a p times 1 minus p plus a 1 minus p squared. So if you keep track of what all was there, you end up with p times 1 minus p. And that's comforting because if you have done any of this stuff before, you might recognize that that's the n equals 1 case of the binomial. You could also perhaps recognize that the binomial is the generalization of a Bernoulli trial, where instead of keeping track of one outcome, you keep track of the number of successes for a set of n trials. All right, so we've done the mean and the variance. Let's go ahead now and talk about the cumulative distribution. So the cumulative distribution is going to be this thing p of x naught, and I use the x naught here only for notational convenience. I've been summing over values of x, and I'm going to keep summing over values of x. And, remember that that's just a placeholder. It tells you what happens when you put that thing in. It's going to be the sum over all allowed values of x that are less than or equal to 0 for the value of the distribution function itself at those points. Okay, so x0 here is a summation limit, and that's it. We have a sum now that's going to end up being a piecewise function. And let me draw the different cases. Okay, if I am at a value of x that's less than x naught, then I didn't hit any of the points that were allowed. And so my cumulative distribution is going to be 0. So this is when x naught is less than the value of 0. All right, let's go back and just make sure we see why that is, okay? So if I take an x naught that's less than 0, the first place where I have a finite probability is at 0. So that's going to give me 0 at that point. And what happens when I just cross through that point, x equals 0, then my cumulative distribution jumps to 1 minus p, the probability of a failure. Okay, and that's going to remain valid until I let x naught become so large that it crosses through x naught equals 1. Okay, so we have x naught less than 1, and anything equal to or greater than 0 is going to count that failure probability. That we have a probability of success that's going to be equal to p, but remember that it's not just p that goes here, it's the sum of p and 1 minus p. Okay, all the probabilities that come before are cumulatively added into this sum. So this is basically happening because we added 1 minus p plus p, and it was equal to 1. And that's going to happen as long as x naught is greater than or equal to 1. Okay, so once we consider values of x naught that exceed the maximum allowed value of x, then we have counted all of the probability in the probability distribution. All right, so I think at this stage we have some idea how the Bernoulli trial distribution works. This is, in many ways, this is almost everything you need to know about every distribution. If you can remember the mean and the variance and the cumulative distribution function, then you're really in good shape for working with that distribution and all the situations in which it arises. The one other thing that we might need to know is a moment generating function, and that would become important if you needed to know moments that were beyond the variance. Okay, so the variance in a sense is like well, technically it's a second cumulant, but it's related to the second moment of the distribution. And in some cases, it's important to know how the distribution is skewed. There are other characteristics that tell you how much it deviates from a Gaussian kind of distribution with only 2 moments. I'm getting way ahead of myself, and I'm sorry. We haven't learned enough to know what I'm talking about, so I'm going to continue on. There we go. All right, so here is our binomial distribution. This is the situation. It is a random variable, y, that counts the number of successes in a series of Bernoulli trials where each one of the trials has the same parameter p. Specifically, y is equal to x1 plus x2 plus, and you continue on going until you get to xn. So this is the shape of the distribution typically. You start at 0, no successes, and you end at all successes. And usually there's some peak somewhere in the middle at a fraction p along the range. So let's go ahead and do our calculations now. Okay, and in this case, remember, this is a sum of Bernoulli trials. So this mean is the expectation value of x1 plus x2 dot 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 to xn. We know something about variables like this. We know that this expectation value represents a sum. And if I take a sum of a linear combination, so this is going to end up being a sum over I equals 1 up to I equals n of the expectation values of each of these individual random variables x sub I. Now, each of the x sub I is a binomial, I keep saying that, I'm sorry, is a Bernoulli trial, and each one has a parameter p. And so what are the values of their means? Well, we just computed that, right? So we just computed the mean of a Bernoulli trial with parameter p and found that it was p. So let's go ahead and put this in as a sum over n of I equals 1 of the parameter p, and that's going to be equal to n times p. That makes a lot of sense, right? At the end of the day, if you flip a coin 100 times and the probability to get a heads is 0.5, you expect if you do it a lot of times, then you will get about 50% of the coin flips to be heads. Of course, you'll get some variation around that, and that's why we have to do the second part of this exercise to talk about the variance in the random variable y. All right, so let's go ahead and do that. Remember that this is going to be the average value of y minus mu y. I should have put a capital Y here. What's the notation we use for that? And we want to do this by over all of the values of y once we know the distribution. So we could do this laboriously. So I could do this by saying the sum over y of y minus mu y squared times py of y. Okay, what's going to go into every one of these terms? Well, this one is just a sum. And in this case, the sum is going to go from 0 up to n. The probability of y is a binomial distribution. And we derived this the other day in class. This is going to be n choose y times 1 minus p to the power n minus y. And that's our binomial distribution. Okay, so this would be one way to go about doing this, and it would take a long time. Okay, we would really suffer as we went through this laborious procedure. Instead, we can remember that this random variable y is a linear combination of other random variables. Okay, so the way we can exploit that is by using these variance identities. We're going to say that if I know that y is comprised of a sum of other random variables, then I can sum over all of those, and they have to be independent of each other. Then I can sum now from 1 to n over all of the variables that contribute to y of their variances multiplied by the coefficients as they appear in the variable y. Now the 1 squared here is because it's just y equals x1 plus x2 plus x3. So each one has a coefficient of 1. And so we're really using variance identities. So notice something here that's very important, and that is that we have changed indexes, right? And this is critical to understanding the mechanics of the step that I just did. Okay, we started out with a summation over different values of y, which went from 0 to n. We can have no successes or we can have all successes. And instead now we're summing over the indexes that indicate which of the independent Bernoulli trials we're talking about. All right, so each of those Bernoulli trials we know has, we've already worked this out in the previous problem, has a variance of p times 1 minus p, and that means that this sum ends up just being n times p times 1 minus p. All right, so this is the variance of a binomial distribution, and that was a lot easier than summing over all of those n choose y terms with p to the y and 1 minus p to the n minus y. So p of y is going to be the sum over all values of y. Let me put a not in here again. Over all values of y that are less than or equal to my y naught. I'm adding up the distribution. So I have n choose y and p to the power y and 1 minus p to the power y. That's by definition what the cumulative distribution is going to be. Is there any way around this? Well, let me just qualitatively sketch. So you saw the shape of the distribution y. You know that the cumulative distribution is adding up each of the columns successively. And so where is the difference between successive points in this distribution going to be largest? It's going to happen when the distribution is tallest. Okay, so this is going to look something like this. At first, the steps are small, and then they become very steep, and then they level off again. Okay, there's our cumulative distribution. It almost looks like a sort of sigmoid curve here. This is right about near the mean of the variable y, and if you want, this distance here is going to be something like 2 times the sigma of y.